Do you remember in my third basic electricity video, Potential Difference, how I discussed the 6 ways to create and maintain voltage? You don't? I'm so disappointed. Well, I'll give you another chance. There are 6 ways to separate the normally equal positive and negative charges that exist in most atoms. The 6 are friction, pressure, heat, light, chemical reaction, and magnetism. Sound familiar? Okay, well, what all those things have in common is that by using them to do work, charges can be separated. When those separated charges flow back together through a wire connected to your electrical device, that work that was done to separate the charges comes back and helps us get something else done. Heat a room, turn a motor, or any one of thousands of other electrically driven tasks. One thing they don't have in common is the way they actually separate the charges. In a battery, the chemical reaction that moves the charges apart results in one terminal that's positive and one terminal that's negative, and they stay that way. In a thermocouple, one end of the heated wire is negative and the other is positive, and they stay that way. We say the polarity of the devices doesn't change. The term polarity comes from the poles of a magnet. So if you connect the device across those poles, current will flow from negative to positive, one way. Direct current, we call it. And we know what happens to that wire as the current flows through it, right? Sure, the wire gets warm from the friction of all those moving charges, and the wire becomes a magnet. As long as the charges are moving, the heating continues and the magnetic field remains in place. Well, what about that 6th way of creating potential difference? Magnetism. In video 3, I explained that relative motion between a conductor and a magnetic field separates charges in the conductor. If we just moved a magnet along a wire, that would do it, but we'd run out of room quickly. So what we really do is spin the wire like this. Well, not exactly. For demonstration purposes, we spin the wire. In reality, the magnet spins inside a coil of wires. Well, 3 coils actually. Please, someone stop me. Okay, the point is, the relative motion we use to create potential difference with magnetism is circular, and this gives a different result from the other ways we talked about. Can you see that if we reverse the direction of movement, the charges would be pushed the other way? A similar thing happens in a generator like this one, except instead of changing directions, the wire comes under the influence of the opposite magnetic pole. The polarity switches, so the current gets pushed first one way, then the other. Alternating current, we call it. So if the source of energy in our circuit is alternating, does the wire still get warm? And what about the magnetic field? Well, maybe a bit more explanation is in order. Imagine for a moment that at a power plant, instead of big generators creating potential difference and causing current to flow in the wires and heat them up, among other things, that there are people pulling on a rope that is threaded in a big loop through a tube that ran to your house, through your devices, and back to the power plant. As long as they keep that rope moving, there's friction and the burner is hot. But what if they switched directions and started pulling the other way? And then switched back? Is the burner still hot? Sure it is. There's still energy being transferred. A couple of not-so-subtle differences, though. If the pull is in one direction only, direct current, the flow is constant. A graph of current flow is a straight line. The magnitude of current is the same at any instant in time, and the magnetic field around the conductor is constant, unchanging, as long as the charges move. Not so with the changing poles. Every time they switch directions, there's some time when the rope slows down, stops, and then starts up the other way. The graph looks very different. This is a sine wave, the graphical representation of voltage and current in an AC system. So when a generator creates potential difference this way, the voltage and current rise to a peak, fall off to zero, rise in the opposite direction, and fall back to zero every revolution. If the generators turn slowly enough, you could watch the lights blink as the generator turned. Every time the sine wave crosses zero, the light goes out. But they don't turn slowly. A big generator like this turns at up to 3,600 RPM. That light is blinking 60 times a second. You don't see it. And the magnetic field? It's rising and falling too, 60 times a second. A moving magnetic field around the wire. Keep it in mind, we'll come back to it soon. But of more immediate concern is this. It's pretty easy to measure the work done by a DC circuit. To determine the work, just multiply volts times amps to get watts. Any time or place we measure them, the current, voltage, and the magnetic field in a DC circuit are the same. So volts times amps here is the same as volts times amps here. The level of work is constant. But how do we measure this? You'd get wildly different readings depending on when you took the measurement. So we have to take an average, but it's not a simple average because of the way the lines curve. The formula used to determine the overall values of current and voltage in an AC system involves a function called root mean square, so the resulting numbers are called RMS values. It's not my intent to go into the calculation. Just understand that this is the way to figure out the effective value of energy in an AC circuit. It turns out that the RMS value is 70.7% of the peak value in a circuit. That makes sense, right? Obviously, the effective value isn't going to be the highest measurement in the cycle because it's only there for an instant. It's got to be something less. So that 120-volt outlet in your house actually has a peak voltage of 170 volts. Insulation values must be based on peak values, not RMS. Most measuring devices are calibrated to read RMS, but an oscilloscope shows the actual wave. And that moving magnetic field around the conductor? It's important also. If another conductor is placed in that moving field, what do we have? Relative motion between a magnetic field and a conductor. All the ingredients we need to, that's right, induce voltage. In future videos, we'll talk a lot more about the implications of the effect, but enough for now. That was an introduction to AC and DC. I hope you enjoyed it. Subscribe to my YouTube channel to see other videos in the series. Thanks for watching.